Good evening. My name is Larry Thiel, Director of the Global Affairs Center here, and I'm just here to call the event to order, and thank you all very much for coming out on this nice, sunny, rainy night. I can't quite explain that, but I'm going to turn the microphone over to the lady here on my left, Paula King. Paula, you got to stand over here where they can see you. She will make a short introduction of the speakers because she knows them personally. Paula and her husband, Brian, who's sitting out there in the front row to my left, co-founded the 350 Seattle Speakers Bureau about 3 years ago. And then they started working with the local NGO, Cascadia Climate Action, to continue the Speakers Bureau. And they recently began another NGO called Seattle Friends of Fission to bring the topic of climate change and nuclear power to the public. And she will explain in her introduction what all these things mean. So I give you Paula.
Okay. Thanks a lot, Larry. And we're really pleased to be part of the Global Affairs Center event, Alternative Energy and Climate Change, the Nuclear Option. I quickly want to bring your attention to two local groups who've made this talk possible, along with Larry and the center. First is Cascadia Climate Action, an independent website that has an embedded calendar with all the local climate change activities listed all in one place. Sort of like one-stop shopping was the idea, to find something to do on climate change. We have been bringing speakers to the public about many issues of climate change for a little over 2 years. And after tonight, our next event is at Naked City Brewery in Greenwood, Monday, April 24th at 7 p.m. It's Hell and High Water, Global Warming and Rising Seas. There's a flyer over there on the table, and there's some small flyers to take away, or you can find it on the calendar. So local effects of rising seas will be discussed with a speaker from the city of Seattle, along with two other people to discuss how climate change creates sea level rise and other local effects on local Indian tribal land. So recently, several of us formed Seattle Friends of Fission to focus talks about climate change and nuclear power. Nick and Scott have done several talks for us at Town Hall, Naked City Brewery, and Ada's Technical Bookstore up on Capitol Hill. And you can find us on Facebook. If you get real excited and want to hear from us some more, we have a sign-up sheet over on the table. So let me encourage everyone, I don't know if you've heard about the Seattle March for Science. That is part of a actually international March for Science. I don't know how many of them are happening, but they're happening all over the world. This one is April 22nd, I believe they're all the same day, at Cal Anderson Park up on Capitol Hill. It's right across from Seattle Central College. It starts at 10 a.m. There's a rally, and that goes until somewhere around 11:30-ish, I think, and then they're going to start marching down to Seattle Center. So you can also, as I said, look at our table over there for some information about Cascadia Climate Action and Seattle Friends of Fission. So now, I'd like to introduce our speakers tonight. Scott Montgomery is an adjunct faculty member at University of Washington's Jackson School of International Studies. He's a nationally acclaimed writer with 15 published books, and his new one due this fall called Seeing the Light, Making the Case for Nuclear Power in the 21st Century, co-authored by Thomas Graham, Jr. He's a geologist who's worked in the field of and taught classes on global energy. Nick Touran graduated from the University of Michigan with a PhD in nuclear engineering. He's working on the design of an advanced nuclear reactor at TerraPower in Bellevue. Bill Gates is part of TerraPower's executive leadership. Nick founded the volunteer-powered nuclear public education website called whatisnuclear.com, where you can find answers to many of your questions about nuclear power. He's an energy enthusiast, a programmer, and always an interesting guy. And Nick's going to start.
Thanks for that intro, Paula. And we're really excited to be here at the Global Affairs Center. Thank you for inviting us. So Paula said most of my intro. Nick Touran. I've been at TerraPower for coming up on 8 years. And my path to TerraPower was basically due to just sort of a simple question I was asking myself, which is how can we power the world at world scale in a way that's responsible and sustainable and without running out of resources? And that's a simple question I've sort of been wondering for a really long time, and it led me to, well, when I discovered nuclear engineering, I discovered it with that question in mind, sort of from the environmentalist perspective. And I was skeptical at first when I was trying to understand what nuclear engineering was as a thing, but the more I learned about it, the more excited I became. And so I decided to learn more and stayed in school for who knows how many years. And then that led me to TerraPower, which is a company whose vision is basically how to produce world-scale energy sustainably. So with this talk, I hope that some of the excitement that I have gained through the years by learning about this, we can sort of transfer to you, and at least, at the very least, inspire you to, learn more about it and read some more stuff. So that's all I want to say to get started, and Scott's really going to get the show on the road.
So let me also tell you where I come from. Unlike Nick, my friend, I'm not paid to do anything about nuclear power. I teach at the University of Washington. I really enjoy it. And I've been doing it for about 14 years. When I was a lot younger, in the Cretaceous period, better known as the 1970s, I was a pretty active anti-nuclear person. I lay down and was taken away to try and stop the building of a reactor at Shoreline. I was a member of the Clamshell Alliance. I marched, I yelled, I passed out leaflets. I was pretty active about that, especially for a graduate student in the sciences. And I didn't change for a long time. 3 Mile Island seemed to solidify things, but then Chernobyl came along in 1986, and that really sort of put the nail in the coffin for a lot of us. And we figured that at that point, the US and a lot of the Western world would turn away from nuclear power. But we didn't bargain on climate change, on the thing that is changing our world today. And I'd like to make a point about that. I have a class that I just left a few hours ago. It's a class of master's students in applied international studies, and they are from many countries in the world. A number of African countries, such as Niger and Rwanda and South Africa and Nigeria. There are a couple of people from Russia, a couple of people from Saudi Arabia. I have a gentleman from Korea. And, oh yeah, I think I have one student from the United States. They are all convinced that China is not changing the Earth's climate. They are all convinced that climate change is a real thing. And for those people that live in Africa, particularly sub-Saharan Africa, particularly in Niger, they've seen its effects in a way that we haven't. Because they've seen people leave large portions of what is called the Sahel, which is just the border region between the Sahara Desert and the region to the south, which becomes tropical. They have seen thousands of people leave their homes and move out of that area as it's become desert. So to them, it's not just real, it's immediate, and it's very, very, very serious, deadly, fatally serious, we would say. Now, when the data came along about climate change, as a geoscientist, I did not bother to look at it. Geologists look at the world in terms of millions of years, at the very least 150,000 or 250,000 years. So climate change on the order of a few decades just does not compute. The climate is always changing, is always changing. And the idea that humanity was doing this, even within 2 centuries, was altering the climate in a very significant way, just did not seem real. But once you begin to look at the information, at the actual data, as I was urged to do later on by some of my colleagues, it becomes quite apparent that this is not a figment of anybody's imagination, that this is scientifically quite real. And the predictions and the forecasts that have been made have been shown to be wrong, not in terms of the level of the forecast changes, but because of the timing, because they've always been behind the curve of what is really happening. I had to change my attitudes about nuclear power for a couple of reasons. One, it is a non-carbon source. It is an existing non-carbon source, not something in the future, something that does not exist. And also because I actually had to think about the numbers. And I'll show some of those to you tonight, too. And they are very, very convincing. I had always thought of it as a very dangerous, risky type of technology. And yet, when you begin to really study how many people have been injured and how many people have died, especially among the public, you begin to see that maybe this isn't really the case. And if you pursue that a little further and look at radiation, something that we all learned to fear quite a bit, I did certainly when I was young, a different story emerges there too. And I'll talk about that with you this evening. So I was asked after the Fukushima accident on March 11th, 2011, to work on a book with this gentleman, Thomas Graham Jr. Now, I'm assuming that most of you haven't heard of him. He was one of the chief United States negotiators for limiting nuclear arms with the Soviet Union from the time of President Nixon up until actually the Soviet Union collapsed, and after that, up until the second Bush administration. So his entire life has been devoted to try and reduce nuclear weapons. And yet, he's extraordinarily pro-nuclear power. And that is not a contradiction. It is not a paradox. They go together very closely. And we'll talk about that too. He asked me to work on this book with him, and after Fukushima, I was a little bit hesitant, I have to admit. But the more I read about it, and the more I studied aspects of nuclear power, not only the past, but the present and the future, what's been happening, what is happening, and what's going to happen, the more convinced I became. And since that time, I've become even more convinced that we are, a lot of us who were anti-nuclear, we were possessed in a certain sense by fears that are not really legitimate. It's not the first time that has happened, and it won't be the last. But I'm going to try and persuade you tonight, at least to re-examine some of the facts, quote unquote, that we have been taught over the years about the dangers of nuclear power. Okay, so I come to this from the point of view of someone who teaches courses in energy and teaches courses about sustainability and about climate change. And so I see this as a very serious thing, I am very beholden to my students, the students that I mentioned today, as well as others that I've taught. This is their enormous issue. This is a lot of your issue. And this is my son's issue. I think of them when I think about climate change, because the world is changing, and we know it is, and we can prove it is, no matter what is said in Washington, D.C., or perhaps other places in the country. This is a real thing, and it's happening, and it's taking lives every year now. And it changes not only the atmosphere, but the oceans, and what is called the cryosphere, of course, the ice that exists on Earth. And it's only going to intensify. It's not on top of our heads right now, but it will be very soon. So when I talk about this, I see young people who I look at every day in class. This is the issue that you're going to have to be struggling with after I'm gone. I'm not making any predictions there exactly, but I won't be around for a huge amount of time. But I am very worried about the future. And one of the things that does have to change is our use of carbon fuels. In essence, if we go back to the year 2000, before renewable energy began its rapid ascent, we were still using the same fuels that we were at mid-century, 50 years before. We had advanced in a lot of our technology, but not in our fuels. And now we know we have to, but this is not easy. This is a major change in world history. The oil and the gas industry alone is a $25 to $30 trillion enterprise around the globe. It penetrates every aspect of our lives. If you think about oil and what it brings us and how it powers transport of every kind. And in international studies, what we think about often is security. So oil is the source that powers every military on the planet today and whatever any military may become, as far as we can see. Turning that huge tanker of $25 trillion of infrastructure around is going to take time. And I can't promise you that it's going to happen in any simple or easy way. It's not. Those fuels support tens of millions of lives around the world and many countries as well. Some of which are our allies, like Norway, and some of which are not. Perhaps we would use the R word, Russia, at this point. But reduce the use of them, we have to do. And it's not going to take just one or two or three sources. It's going to take every source that we can make commercial. Now, as we'll repeat, one of the numbers I would like you to take home is 62.5, because that is the percent of non-carbon electricity that nuclear provides for the United States right now. And if you take that away, that's an awful lot of power to replace. And I'm afraid renewables are just not up to the task yet. They will be. They will be. There's an awful lot of money and intelligence going into them. And this brings up a theme for the two of us, and that is that we do not see nuclear as a solution. We see it as an essential part of an essential solution. Renewables are no less essential. They need to work together. We need to make use of the non-carbon technologies that we have, and we cannot afford to throw any of them to the side or ignore them. This is our probably main message tonight. Renewables have certain limitations that nuclear can make up. Nuclear has limitations that the renewables can fill in. They need to work together. And energy experts are coming to the point where they recognize that this is probably the only way that we will get out of this predicament long term. Now, we're going to show you some slides tonight, and we're going to try and answer some questions before you're able to ask them. But we really want to hear from you too, what you want to know. And we will answer your questions as best we can. We make a request that you don't attack, that we offer this information up here in good faith. And so we're not up here to debate in a very angry fashion. That really doesn't get anything anywhere. And I've spent too much time doing that already. The one other thing that I'll just mention at this point is that for about 30 years, there was an excellent science writer who wrote on energy issues for the New York Times. His name was Matt Wald. For 30 years, his articles were the ones that I would go to get an unbiased view, someone who really took the time to research his subjects. Whether it was wind power or whether it was gas, whether it was fracking, whatever it might have been. Now, he left the New York Times last year. And very interestingly, he went to work as a public relations person for the Nuclear Energy Institute in the United States. Now, why did he do that? He did that because he feels very strongly in the same types of ideas and perceptions and truths that we do. that we're not going to be able to take care of climate change and some other very nasty, lethal threats that exist around the world, including air pollution, unless nuclear power is maintained and perhaps expanded as well. And so with that, I think I'm going to turn it over to Nick, who's going to talk a little bit about the history of nuclear energy and try and bring you up to speed with that.
Where's that clicker?
Here it is.
Thanks. Right. Thanks, Scott. So yeah, I just want to briefly give you some context of what exactly is nuclear energy and where did we find it. History is fun because you just have to pick a spot to begin because it's all building on the previous thing. So we're going to start with X-rays, which were discovered in 1895 by Wilhelm Röntgen by applying high voltage to some vacuumed out glass chambers. He found that these X-rays would come shooting out and you could see through things, and that actually led to this sort of X-ray mania where the whole physics community, which is like 20 people, were investigating them. And within the year, this guy on the left, Henry Becquerel, discovered that sometimes certain materials that have uranium in them occasionally emit something that looks a lot like an X-ray without any high voltage applied, just totally spontaneously. That was pretty interesting. And so Marie Curie and her husband Pierre systematically studied it and named the phenomenon radioactivity. It basically implied that there's things smaller, there are subatomic particles, which led to all sorts of other investigations. And so people discovered protons and electrons, and 30 years later they discovered the neutron, which is the neutral version of a proton you probably heard of. And so when that was discovered, people started shooting it at all the different materials they could find, as you do when you discover a new particle. And something interesting was discovered, which is that sometimes if you shoot a neutron at a certain type of atom, a uranium atom, occasionally it just splits right in half. It doesn't shoot off a little chunk of itself like this natural radiation, but it actually just splits in half, and that's called fission. And that releases an astounding amount of energy for an atom, 2 million times more energy than you'd get from sort of an equivalently sized chemical bond. Of course, it's just one atom, so you wouldn't be able to feel it because you're made of 10 to the 24th atoms or so. So maybe no big deal. But there was sort of a double miracle, which is these extra neutrons also are emitted when that atom splits. And because of those extra neutrons, one of those can go on, if you put another fuel atom nearby, you can cause a nuclear chain reaction. And that then can release a macroscopically tremendous amount of energy, which is the key, which is what we use in a nuclear reactor. Now, how much energy is this? So this is kind of the key of why nuclear is interesting to me, is because of how much energy you can get out of this stuff. So just as a quick demonstration, these are coal cars. You've probably seen these huge train cars full of coal. If the world got all of its energy from coal, which it doesn't, but if it did, this is just a visualization, it would be currently burning 5.5 of these train cars full of coal per second. So you can kind of imagine that by like clapping it out. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's how many coal cars are being combusted in the world furnace. Again, if it was all coal. Now, if you had or if you had these train cars full of uranium, you'd be using 1.5 of these per week. So instead of 5 per second, it's just 1, and then see you next Friday for the next one. And this represents all the uranium you would need to power the entire world for 1 year. And that, to me, is just extremely exciting because that implies a footprint. If you can get that much energy out of that little stuff, you can do it with a very low footprint. You don't need huge transportation infrastructure. You don't need huge mining infrastructure. Assuming you can build machines to extract the energy with reasonable footprint, the nuclear reactors, this can be an extremely responsible and scalable energy source. And again, when you split an atom, this reaction doesn't emit carbon dioxide, it doesn't emit particulates, it just has these 2 half atoms, which you may know as nuclear waste, and we'll talk more about that later. So anyway, another representation of this is made by XKCD, if any of you are readers of this webcomic. He says, science tip, log scales are for quitters who can't find enough paper to make their point properly. This is showing how much energy is in a kilogram of different fuel sources, and this is the uranium. You can see it's just in a class of its own in terms of how much energy is in that stuff. So how do you get that energy out? You use a machine called a nuclear reactor. And this is just one representation of a common type of nuclear reactor. You put the nuclear chain reaction in this machine and it starts sustaining that reaction. That just heats up some kind of coolant, in this case it's water, and that water goes through this primary loop and it does the most exotic thing you can imagine. It boils water. And that water turns into steam and goes through this big pinwheel-like thing, the steam turbine, which is hooked to a generator, just like your alternator in your car, and that powers the city. So that's the basic workings of, there's lots of different types of nuclear reactors, more on that later, but this is just the basic concept. You sustain a chain reaction, you heat up a coolant, you spin a turbine, and you make electricity. You also could make propulsion for a submarine, which is one of the first things that was done with this, or a couple other applications, but this is how you make electricity. Okay, so that's just that context, and I'll pass it back to Scott.
By the way, there are many, many nuclear plants around the world that have 2 or 3 reactors. Some of the more recent ones, of the examples of those, can power an entire city, between 2 and 3 gigawatts of electricity. San Francisco uses about 2.5 gigawatts. The largest reactor we have in the United States has 6, and it's called the Palo Verde, and it's in the center of Arizona where there's no water. Where do they get their water from? Wow, how did they do that? Well, we'll have to find out a little bit later. So you've all seen pictures like this, right? And it's almost a bias at this point that we would think that this is China. This is not China. This is India. India now has half of the dirtiest air cities in the world. And the same thing is happening there as happened in China. India is powering a great part of its economic development, particularly in power generation with coal. Why does it do that? And why did China do that? And why does Indonesia think about doing it? And why does Vietnam use so much of it? And why has Turkey used so much of it? And there's one very simple answer, and I could go on and list a number of other countries. Because they have it. Because it's domestic. It's within their borders. It's within their control. And so they consider this a mark of energy security. We got it. We can use it. But as China has taught the world, although China could have learned from what the West had done, frankly, those beautiful Monet paintings that you've seen, perhaps, of the London fogs in the late 19th century, those were killer smogs. People died in those because it was coal. It was particulate matter, matter that gets caught in your lungs. And if you have tuberculosis, like many people did, that can be quite lethal. But we learned this lesson again from China. China today is estimated to be losing between 1.5 and 2 million people a year prematurely due to the coal and the smog, the coal smoke and the smog that exist in its cities. India is catching up. India is somewhere between 250,000 and 500,000 people. That's a lot of people. That's more people in a year that died in Hiroshima and Nagasaki. And so, in a sense, we make these comparisons not to be morbid, but to point out the lessons we've learned about coal and air pollution. We thought air pollution was something that could be easily gotten rid of. But more recently, the World Health Organization has done a whole series of studies of this around the world and come to the conclusion that particulate matter, very, very tiny, unburned portions of these fuels, coal and oil particularly, but coal above all, are responsible for up to 5 to 7 million deaths every year. indoors as well as outdoors, and that air pollution is a lot more serious and a lot more lethal than we ever thought, even in the past. So this is another reason to replace coal. Another reason why non-carbon fuels are needed. So this is a picture in Delhi, which now is one of the top 3 cities in the world for air pollution. I'm going to talk a little bit about where nuclear is right now. This is a graph put together by the International Energy Agency in a document they produce every year called the World Energy Outlook. It is a combination of information that is supplied by governments all over the world, 150 countries, to allow the IEA, as we call it, in Paris, to put together this report that shows where the world is with energy and where it's headed. And each time they put this out, and it's quite large now, it's over 1,000 pages, they'll focus on another area of the world. And they've done this on India and China, and most recently on Africa. And what they've done here in their 2014 edition is to draw everything back to 2010. Let's say we start there at 0. And to project, based on all the information that's available, who is going to want to expand their electricity, their power generation the most. What's interesting about this is that here's the OECD. Does everybody know what the OECD is? Okay. The Organization for Economic Cooperation and Development. Now you know, right? You know exactly, yes. Those are essentially the wealthy countries of the West, plus Japan and South Korea. So there are about 35 countries involved. They're the ones that controlled the energy universe for 200 years, since the very beginning of modern energy use, the beginning of coal use in the Industrial Revolution. Their time as being the center of the global energy universe is over. Okay, we, if I can say that, in the West no longer control consumption or demand. That control has passed to Asia. In the future, Asian countries are the ones that are going to demand an enormous increase in power. We, in the West, increase very slightly. This is a major change in human history, in modern history particularly. So our time when our demand for energy was going up and up and up is now over. Now we're at a plateau. And this is quite interesting. For China, an enormous increase, but with India, the two of them, almost as large as the rest of the world. But this is other developing Asia, is the pink here. And then we have Russia, and then the rest of the world. Okay, the rest of the world, or better known as the ROW countries, they are very large. But you'll see this goes to 2035. And it continues, obviously, into the second half of this century. So who is going to control? What countries are going to make the major decisions about the fuels that will be chosen? The history, or the future history, let me put it that way, of carbon use does not lie in the West. Okay, and so these questions are absolutely crucial for the future of climate change. Okay, now this is a map that I put together. It's called Nuclear Power of the World. Each one of the countries on which those stars occur are countries, well, the vast majority of them are countries that are expanding their nuclear programs or starting it. A large number of these countries, particularly in Africa, but also in Southeast Asia, have no nuclear power right now. They want it. One of the reasons is that the de facto, or I should say the default choice for these countries is to either go with nuclear, with natural gas, or with coal. Coal is the cheapest. It is the most abundant, and a fair number of countries in Asia have this. Nuclear is the most expensive, but it is also the source of the largest amount of reliable electricity, and that's what a lot of these countries need. They've reached a point where their economic growth has stalled, and the reason for that is they don't have enough electricity. A lot of them have based this on hydropower too, and that's a very uncertain source for the future given climate change and the droughts that can happen. But all of these countries with the smaller stars have started now nuclear programs. They do not have nuclear reactors. Most of them are not building them, but they are making deals with exporters. Who are the exporters? South Korea is one. South Korea is building right now nuclear power plants here in the Persian Gulf with the United Arab Emirates, building 4 of them, very large plants, 1.4 gigawatts for each one. Very interesting. The Persian Gulf now has 2 countries with nuclear power. The first one of those reactors will go online this year. But Saudi Arabia is interested, Kuwait is interested, Egypt is interested, Algeria is interested, Qatar is interested. Why are all these countries that have oil and gas interested? They're interested exactly because they have oil and gas and they're burning it up for their own electricity. They want to save it for export. These are countries that have not diversified their economies very much. And they're looking into the future. And they see climate change as something that's going to affect their part of the world very seriously as well. They already have serious water problems. So they're looking at nuclear not only as a source of electricity, but also as a source of heat that can be used for desalination. Looking at multiple uses of this. Okay, now I've obviously made China quite large because China is one of the exporters. South Korea is one of the exporters. Russia is one of the exporters. I should have put one on Canada because Canada is one of the exporters. And potentially France is as well. India is one of the large importers. All of these countries are expanding their nuclear programs. The one country that is not an exporter is the United States.
When you say exporter, you're talking technology?
I'm talking technology. I'm talking about building reactors in other countries. Yes, thank you. Okay, so a few other pieces to this. Today we have 450 operable reactors. 3 years ago it was 439. So it is expanding. We have 60 under construction. There are 165 more that are on order. And there are 350 beyond that that are proposed. This is the situation right now, as it is reported by the countries themselves. There are strong possibilities that China itself will have hundreds of reactors by 2040. There are a number of reasons for that. The reason this is important is because if you were to look at these numbers, certainly this number, and this number, 10 years ago, they would be much closer to 0. Or let's say 20 years ago, they would be much closer to 0. This is a new nuclear era that we are in. The West has not joined it yet, but it is happening, and it is moving ahead. China is building between 5 and 8 reactors every single year. Russia is building 1 or 2. India is building 1 or 2. This is a new era. And inasmuch as the West is no longer the center of the energy world, it is no longer the center of the nuclear world either. It has a choice to join this new age or not, or to give up for various reasons, whether they're economic or whether it's due to fear, a non-carbon source. In fact, the major non-carbon source. 15 minutes left. Oh dear, okay. So these are new reactor construction starts. I just want to show you that this is going on. 2017, the promise is to have 14 new reactors enter construction this year. This is Ontario. Ontario is the first large political entity that has done away with coal entirely, and it has done that with a mixture of renewables, hydropower, and nuclear power. So our neighbors to the north have done something. This is a very important precedent that I just wanted to point out. Okay, so these are some numbers. Again, 62.5% is one, but here are some other numbers. 300 reactors have been operated over the last 50 years. That's an average. And of those reactors, and of the 3 major accidents that have occurred during that period of 50 years, there have been about 50 to 55 deaths. No more. No less, but no more. And this is worldwide. So you have to ask yourself, is that a dangerous technology? Let's look at the numbers for the US. 70 reactors averaged over this period of 60 years, and we have not had a single death among the public. Not one. Not an injury either. And I ask you, is this a dangerous technology? 3 Mile Island did not injure or kill anyone. There have been 12 lawsuits filed to try and prove that it did, and every single one of them has failed on the basis of scientific information. This is not just information that comes out of the air. This is information that is now well confirmed in the scientific community.
Can you remind us about Island, when and where?
3 Mile Island is, I assume everybody knows about TMI. Have you all heard of 3 Mile Island? Yeah, you've all heard of it. Yeah, so it's near Harrisburg, Pennsylvania. It's on an island in the middle of the Potomac River, and there are 2 reactors there, and there was a partial meltdown of one of them in 1979, 2 weeks before the movie China Syndrome came out. And you thought Hollywood wasn't clever. Okay, so no, they didn't do that. Just a couple of more things very quickly. You probably have seen this. This is an iconic image of Chernobyl. Okay, Chernobyl, the most serious reactor accident by far. Reactor accident that couldn't have happened in the West because we would not have built this type of...
Where?
Hmm?
When and where?
Oh, excuse me, sorry. 1986, in the town of Chernobyl, near Pripyat, another small town about 75, 80 miles north of Kiev. It is now in the Ukraine, no longer in the Soviet Union. Thank you. So there have been 3 decades since that accident happened, and there have been thousands of scientists who have worked, who have studied the impacts of this. These are not scientists that come from the nuclear industry. These are scientists that work in a whole series of UN agencies and for a variety of different universities. The total number of deaths is about 56. That's my number, and I project that as 56 because a couple of the workers who had gone in to take care of the fire, who were not told about the radiation and given no protection at all, some of them were exposed to very high levels of radiation that normally would cause leukemia or serious solid cancers. They have not contracted that yet, so partly I am predicting that they will, but it's 30 years later. Now, in terms of modeling, because there are various ways of estimating who will, or how many people, how many excess cancers will occur, the models predict 22,800 extra cancers, cancers beyond those that are predicted to occur on the basis of cancer rates, and this is for all of Europe, for 570 million people. And that is 22.8 thousand in addition to the 194 million who are expected, because there's 25% to 27% cancer rate in Europe. Okay? But
194 is not Chernobyl.
no,
22.8 is.
only 22.8 thousand. Right. And you can see this. There's a well-known book about radiation called Strange Glow, written by a radiologist who's head of the radiology department at the Georgetown University. It's Timothy Jorgitz. It's an interesting book. But the final conclusions, which are often discounted by the anti-nuclear groups, are quite striking to read. It's not the radiation. It's the actual fear of radiation and the stigmatization. This is showing up in Japan, too, today, that causes the worst health impacts. And this is very well studied, and the studies will continue. So just a few other things. Oh, yes, of course. And then when you yank people out of their lives, you get some serious impacts. In Fukushima, people were pulled out of intensive care and critical care facilities and in live-in assistance situations as well. That was a panic evacuation in Fukushima. Okay. By the way, Chernobyl, the exclusion zone around Chernobyl now is the largest wildlife preserve in all of Europe and all of Eurasia. The animals have come back in a major way. This is within the exclusion zone, meaning you can't go there without a permit. Well, you could go there with a tour guide because they run tours. They take you right up to the reactor. Did you know that? Yeah. You can go in there. Now, you can't sleep overnight or camp for a week or anything like that, and there's some areas that they want you to stay away from for more than a few minutes, but yes, there are tours there. But the animals that have come back are quite striking. Some of them were driven out of the entire area, like the Eurasian lynx. And this particular species of owl was extinct in that area and has come back. So this is an interesting development. Okay. Okay, so
10 minutes.
okay. All right. So quickly, this is a nice beach in India along the Malabar coast, which is in the southwestern part. People are not dropping dead on the beach, and yet these are the most radioactive sands that exist on Earth. They are 5 to 10 times higher in their radiation than what is allowed for nuclear power plant workers on a yearly basis. And yet this is a very famous resort place, and people go there every year. Cancer rates, yes, they've been studied. Are they much higher? No, they're not higher at all. If anything, they're slightly lower. This has been studied again and again and again. Now, this is not the only case. Okay, there's another area. This is Ramsar, Iran, and the northern part of the Elbrus Mountains and the southern coast of the Caspian Sea. They have radium springs here. This is a hot springs area, and a lot of the middle class who can afford it and the wealthy from Touran during the beastly heat of the summer, they come to this area because they get breezes off the Caspian Sea, and then there are these wonderful hot springs. The hot springs, when they overflow and the water evaporates out, creates a very interesting type of rock, travertine, very highly radioactive, but the local noble palace was built out of that. Now, this has radioactivity that is 4 to 5 times as higher than those sands in Kerala, India. Much, much, much higher than is allowed for the public. Very interesting. So I'm a geoscientist, and we like empirical information. Models are great, but you gotta have on-the-ground data from the real world, right? That's real world information. and is not yet explained very well by the models. Okay, so very quickly, these are dose levels. They're called sieverts and millisieverts. The dose levels actually incorporate ideas or estimates of the biological effects on human beings. The average for the world and the average for the United States is about 2.4 to 3 millisieverts. Okay, so let's take a look at some others. This is Finland. Finland has lots of granite, lots of metamorphic rock. Granite is a favorite place for uranium and thorium. They have the level of about 35 up to about 40 millisieverts. Not everywhere, because different places in Fennoscandia have different amounts of granite, but this is significantly more than the United States or the world's level. This is Kerala, India. Kerala, India is between 75 and 100. Okay, so quite a bit higher. Quite a bit higher. And what about Ramsar? That's above 200. Now, these are levels that you will be told are very dangerous for you. And yet, people who live in this have never had problems, do not have cancer rates that are higher, do not die at earlier ages, do not get more diseases. This is the level at which the Fukushima evacuees were exposed, about 20 and under. Okay? And this is the level that the government said had to be reached before they could go home, before it was safe. That character there, I put that up there for some Chinese students that I had and some Japanese students. It means to return. So I'll let you make up your own mind about whether that was something that kept people away from their homes years longer than they needed to be or not. And this is a CT scan. So the Japanese that fled their country and came to the United States, and let's say they went to Denver, because Denver has about between 5 and 15 millisieverts. They received more radiation here than they did, especially if they were from Tokyo, because Tokyo was very slightly affected. So this is the kind of thing that led me to question all of these warnings that we have been taught about the dangers of radiation. Oh, very quickly, fatalities in the oil and gas industry, yeah, there are thousands every year, between 1 and 800 in the United States alone. What about the wind industry? Oops. More than 150 fatality. How do you die? Well, you fall off. Or in a hurricane, they don't stand up very well to very strong winds. Now, this is not a criticism of the wind industry. Every energy source has its limits. But there have been accidents, and more people have been killed by wind turbines than have by nuclear power plants. Okay. And this last part. So this is where you come to be when you start to study this. Okay.
Okay, so we wanted to leave some time for questions, but we're almost at question time. But I would like to, I'm going to try to rush through these relatively quickly. I want to talk a little bit about problems and solutions with nuclear. You have a bunch of questions in your mind, right? Like, just yell it out. What about the waste? Yeah. What else? Lifespan of the plant. Yeah. Okay.
Various types of radiation.
Right. Different effects from different natures of radiation.
Funding for national laboratory research.
That's a good one. March for Science.
Yes.
So, right. So a lot of these issues, so waste and safety are two that come up a lot. And Scott just kind of went through a reasonable argument about safety. Let me just point out one issue. This is kind of the crux of safety and waste. If you have an operating nuclear reactor at 100% power, and all of a sudden you decide to shut it down by inserting the control rods, the chain reaction stops, and so what's the problem? This happened at Fukushima, for instance. The control rods went in after the earthquake, the chain reaction shut down, so what's the problem? Well, turns out there's this thing called decay heat. It starts about 7%. Not all the energy in a nuclear fission reaction comes out at once. Turns out about 7% of it comes out later with time, and that's called decay heat. And you have to cool that decay heat in order to keep the fuel systems from melting and releasing the radiation. So that stuff this is also the same heat that is what makes nuclear waste dangerous. Okay, so this is the fundamental sort of issue with nuclear technology. So, but it turns out, as Scott pointed out, that it's actually extremely safe. And another way to look at that is to just say that this is a study by James Hansen, who's one of the key climate scientists who's pushed to help publicize the issues of climate change since the 80s. He did a paper in 2013 that showed that nuclear reactors net have actually saved 1.8 million lives simply by displacing air pollution deaths that would have happened had the average energy source occurred or been built. So it is extremely safe, and this is just another data point for that. In terms of just operational safety of the plant, that decay heat I showed, a typical reactor requires backup diesel generators, power from some off-grid power to run pumps that cool the system to keep that decay heat from melting anything. But it turns out there's a bunch of other types of reactors that have been built and proposed. And this is a picture of one called EBR-2 that was operated in Idaho from the 60s to the 90s. And this reactor is an advanced liquid metal cooled reactor that has an interesting capability. It can cool itself completely naturally without any backup pumps or diesel generators or anything. It just uses natural circulation, and it dumps the decay heat straight to the air in almost any scenario. This actually was demonstrated when they ran a situation. Not only can it cool the decay heat passively, but it can also shut itself down without even inserting the control rods. So they did an experiment in 1986, weeks before Chernobyl actually, where they just were running the reactor and they turned off the main pump and didn't put the control rods in. And that would cause a typical reactor to go through all sorts of active safety systems to shut it down and push those control rods in. But this reactor, those control rods have just naturally shut down, decreased in power, and then dumped its heat to the environment totally naturally. So there are reactors out there. Now, so traditional reactors now are one of the safest energy sources we know, but if you want to scale up to world scale, you have to make thousands of reactors, and you can't afford, well, it's safer than basically any other energy source, but you don't want to have a Fukushima every 10 years or every 20 years. You want to get that down even farther, arguably, although Scott might question that. And so there are advanced types of reactors out there that are capable of getting to that level of safety, and that's the kind of reactor that I spend a lot of time working on. All right, so one more reiteration. Scott mentioned this. Of all the sources of electricity in the United States that are non-emitting, which are these guys, hydro, solar, wind, and geothermal, and nuclear, nuclear is the biggest. Nuclear is currently the climate champion in the United States. And this is something that I don't think a lot of people realize. This is the total, the rest of it is natural gas and coal. And so this is something, when you're hearing about nuclear reactors shutting down, like you're taking this chunk out and it's almost always being replaced mostly with natural gas. And although renewables are increasing relatively rapidly. Okay, and another thing, some people say, well, what if you run out of fuel? Well, nuclear is extremely sustainable. I mentioned how much energy is in that fuel, and there's actually a huge amount of fuel known in the world. So just rest assured we can run the whole world with a substantial growth rate for hundreds of thousands of years with the known resources, especially using some of the advanced reactors like a breeder reactor. as opposed to the reactors we have running today. There's also an unbelievable amount of uranium dissolved in seawater, and scientists at the Pacific Northwest National Lab and other places are working on ways to extract that, basically farming it with polymers that absorb the uranium. And the prices of that are still more expensive than mining uranium directly, but they're not that much more expensive. And it's reasonable to imagine that we'll be able to sort of harvest uranium out of the ocean passively. And if we do that, we have, it's nearly a renewable resource that lasts for billions of years at world scale capacity. So that's pretty exciting. Another thing people are concerned about, rightly so, is nuclear weapons. What's the association between nuclear reactors and nuclear weapons? They have a bit of a shared history. I mean, that nuclear reactor, first one was operated in 1942. It took the Manhattan Project to weaponize that, and there was a huge amount of work in the Manhattan Project that went into taking a nuclear reactor that was stable and operating and turn it into an explosive. But there still is some overlap in fuel cycle, such as enrichment capabilities can be used kind of for both. But one thing people don't know that I think is really exciting is there's this thing called the megatons to megawatts program that was in place from 1993 to 2013. This was a program where the United States bought dismantled Soviet nuclear weapons that were downblended. They took the highly enriched uranium and blended it with low enriched uranium and then sold it to us. We stuck it in our nuclear reactors and burned it to make electricity. And that was such a huge program that 1 out of 10 light bulbs in the country was powered by dismantled Soviet nuclear weapons. For 20 years, 10% of our total electricity. It's pretty incredible. So nuclear reactors are actually a fantastic way to fundamentally destroy nuclear weapons and get rid of stockpiles. So that's just kind of a fun fact. Yeah, so let's see. So there are 25 minutes left, and we have more slides. What do you want to do?
I want, people talked about the waste. I have just a couple of slides on the waste. Would that be okay to, and then we can go ahead?
Keep going. Okay.
This is not the waste, this is a gas explosion in Connecticut that you never heard of. It killed 6 people and more than 30 were injured. That was in 2010. If that had been a nuclear reactor, every one of you would know every detail about it, but you know probably nothing about it. I didn't. Okay, so let's go ahead. And you may remember the Oroville Dam, but we're going to go ahead. Okay, CenturyLink field. What's that box doing there? That box is the volume of all the nuclear waste that has ever been produced in the world from the time when the very first power reactor went online. That's the scale of it. The US has about 1/4 of that. So chop off about 1/4 of that. Now when you compare that, and that's nuclear waste, okay, that's waste that has gone through the reactor just once. And so we've only gotten only a few percent. This is quite literally true. Only a few percent of the energy content in that material has been derived, has been used. If we put it into what is called a fast reactor, we could get up to 90%, perhaps, much, much more. But those have been off the table for a while. There's a big concern about plutonium. The plutonium that we have here, which is about 32 metric tons, would be about this much of the square. And though plutonium, yes, it can be used in a weapon, absolutely. We have chemical weapons that are lethal. Yeah, I know, we're not supposed to have them, right? We have chemical weapons that are 100 times that volume, and yet they're under lock and key. We also have biological weapons that are much larger than that in laboratories. They are under lock and key. If we can't somehow protect something of volume that's that small in a country like this, then we have a problem, because we're doing it all the time with other lethal materials. And plutonium is not more lethal than a number of the chemicals that we would use as weapons. Okay, so that's one aspect. This is, by the way, the waste from a single coal plant in Tennessee over about 50 years, the Kingston coal plant, one plant. And, oh, I forgot to put this up here, I'm sorry. That's the nuclear waste that would, by comparison. Now this collapsed in 2012 and flooded through a small town. Coal waste, as you may or may not know, has some really nice things in it, like arsenic and mercury and selenium and cobalt and cadmium and a lot of other things that you don't really want in your sandwich. By the way, this is a truck, small pickup truck. That gives you an idea of the scale. The coal waste that we have in this country that is allowed to stand out in the open is a tremendous scandal. We devote an awful lot of fear towards nuclear waste while we leave this kind of material around. A double standard? Perhaps, in some ways. Okay, so that's all. That's just the talk about waste. So now it's up to you. What questions do you have? And we hope we can answer them. Go ahead.
Thank you. So where did all of this concern about radiation being so hazardous come from? It had to come from someplace. Can you please go on?
So there's a history to it. In part, it has to do with the association of anything nuclear with Nagasaki and Hiroshima, with the weapons. But there's also a history, and our book will talk about this, that came from the fallout controversies in the 1950s, the weapons testing and how that impacted people on the Marshall Islands, and of a very famous episode called the Lucky Dragon episode, which was a Japanese fishing ship that got into the shadow of what was called the Castle Bravo nuclear test. It was the first test of a dry thermonuclear weapon. And it was very successful. In fact, it was twice as successful as they wanted it to be. It had 2 times the amount of megatonnage, 2 times the yield of what people predicted. And it cast a very large fallout shadow. And it poisoned 27 men on this ship, and they came down with acute radiation sickness. And that means you lose some hair, you have bloody diarrhea, you're very sick. It does not mean you die, and none of them, it seems, died from the radiation, though one of them did die from blood poisoning. But this was a big cause célèbre in the United States. And you can imagine Japan, not many years before. This was in 1954, so not even a decade since they had been bombed. And then here they're suffering again. And so this was a huge cause in the United States. The other part of it was that the Atomic Energy Commission, which was in charge of weapons and reactors at the time, one of their directors blatantly lied about the dangers of fallout to the public again and again and again. And some of the scientists, such as Linus Pauling, came out and sort of pulled the veil over that. And this had a real impact on the public and on the media as a whole, that these things were a lot more dangerous than we've ever been told. We've been lied to. We can't trust the government about this, no matter what they tell us. And so even though the Atomic Energy Commission did say some things that were true, and then when it became the Nuclear Regulatory Commission in the 70s, and also said that, you know, this is just not as dangerous as you think it is, no one believed them. It was the wolf story, right? The wolf at the door. And that has had a real impact on the media and on all of us, especially those of us that are, you know, from the Cretaceous period. But it stayed with us a long time. And it has been repeated at every single time there's been an accident, even a very small accident. And there's also another aspect to this, and I'm going to have to say this, sorry, because I'm a Democrat myself, born and bred, and though because I'm a pro-nuclear person, I'm called a bad liberal sometimes. But Democrats as a whole are against nuclear power because they feel they've been the inheritors of this tradition, that it's risky, the waste is too dangerous to deal with, and we have safer things to use. And it's very unfortunate, but they've had a real impact on the ability to maintain the reactors that we have and on the funding of some of the really very top level research institutes at Oak Ridge in Tennessee or Argonne and Brookhaven and other places. So it's a complex thing and it's a historical thing. But we can turn it around. Knowledge can really turn it around. And that's why I'm up here, because it really turned my head around. And I feel I have more of the truth now than I did before.
We'll take the next question.
Right here. So looks like nuclear power has very good sides and not as many drawbacks. So I'm from Barcelona, and like 200 miles from Barcelona city, they are about to create what we call in Spanish a nuclear graveyard, where they bury all the nuclear waste. So people around that area, the towns, and they are really scared about that because these things are toxic for millions and hundreds of millions of years, and so is there's really a reason to be afraid of this waste when it's buried by tons of concrete
Right.
but knowing that you're living close to something that is toxic and dangerous for hundreds of millions of years?
So, yeah, and that's a common issue. We call it not in my backyard. And we've had trouble in the United States citing waste repositories, we call them. Basically, the geology of it, like we know scientifically that we can store that stuff underground safely for the time required for it to decay back to the level of it before it came out of the ground. And there's a site in the United States called the WIP, which is in deep salt, which is good. Yucca Mountain is not necessarily the most ideal site. The site in Barcelona I'm not as familiar with, but the science behind storing waste is extremely well understood, and there are very reasonable assurances that there's nothing to be afraid of. When it's buried, it's not going to come out and get you. There's much worse things that are coming from the other energy sources, such as air pollution and climate change, that are real present dangers. And putting the nuclear waste in the ground isn't just kicking it down, kicking the can for future generations. It's actually a reasonable technical solution. The thing we haven't figured out is the political solution, mostly because people are afraid of the radiation.
Yeah, he's right. One other thing. This is Finland, and they have solved the problem. And this is a site. This is a schematic of the repository rather than graveyard. But it's at a site where there's a nuclear reactor and where the local community is completely in favor of nuclear power. It's given them jobs. It hasn't killed anyone or injured anyone. Everything is kept very clean. I mean, it's Scandinavia, right? So, but they are very much in favor of this repository there. All countries need it, but it is not a technical problem. As I say at every one of these talks, the United States and many other countries inject underground millions to billions of gallons of dangerous toxic waste every year. And it's not a problem to store material underground. I'm talking about non-nuclear waste. And the chemical companies have their sites. And there are many regulations behind these. But people are afraid of nuclear waste much more than they are of anything else. Now, if you ask me, would I have it in my backyard? You know, yeah. Why? Because it's 1,000, 2,000, 3,000 feet below me. I'm not going to see it. And there's so many regulations about how to do it, I'm not going to worry about it. If someone says, you know, we're going to pump, you know, a bunch of toxic chemical waste down a well underneath your house, maybe 2,000 feet into a nice sandstone reservoir, I'm going to say, no, you're not. Because they can actually leak, but these repositories won't.
One interesting thing, sorry about the other questions. You may wonder, how do we know how radioactive nuclides move for millions of years? Well, there's this one interesting data point we have where there was actually a natural nuclear chain reaction 2 billion years ago in Africa, and we can actually look in Ghana, and we can look at, we can see how far various radionuclides migrated over billions of years. And so using that can validate some of the models we know about how far things are going to go in certain time frames. And that provides a lot of actual experimental data to some of the claims we can make about the very long time scales in certain rocks. Anyway,
The
other
Soviets
questions?
had an explosion from overstorage.
At the Mayak complex, at Kishtim, yeah, in 1957. Does that answer your question?
Yeah, I was a little short one. Since Fukushima happened, sort of the earthquake.
Can't hear.
Wait a minute. Tim, can you keep your answers a little bit shorter if we really want to end this?
Yeah, all
I
right.
see a lot of hands up.
Yeah, there are a lot of-
It's a really short one. The amount of time to cool down the reactor is shorter than the time scientific people need to detect that is going to come an earthquake. So do we have enough time to power down the reactors and cool down and evacuate the people or whatever? I mean, before detecting we have an earthquake coming? Earthquake? Yeah.
So the early warning, they have all these detectors around the plant. They can see the earthquake coming, and they shut it down as it was happening, and it totally shut down perfectly safely, and all of the safety systems kicked on to start cooling it. The problem was when the tsunami came, they didn't put their fuel source high enough for their backup generators, and the tsunami flooded their fuel source and some of their electronics that shut down their generators. Plants are not supposed to fail in these kind of scenarios, so all you have to do is make sure either you don't require backup safety systems by making advanced reactors, or making more robust safety systems, as all the reactors in the world have done as a response to Fukushima.
The other answer to that is that there were 12 other reactors that shut down safely.
Yeah.
That was the only one that had a problem. And most of the others had their emergency generators up higher.
Who's next? Sorry.
Well,
I have two questions. The first one is why don't we have thorium reactors yet? And the second question is, can the method of vitrification, which is like mixing with glass, ever be widely applied? Because it's a very interesting theory.
Right.
Thank you.
Great question. So I didn't get to my thorium slide, I'm sorry. So thorium is another fuel source like uranium. There's lots of it in the world, and especially in places like India. The most likely place you'll find a thorium reactor in the future is in India because they have so much of it.
those sands were thorium
Right.
radioactive.
There are some advanced reactors that work very well with thorium, like the molten salt reactor, which uses a fluid fuel. It's in the class of advanced reactors that doesn't need backup safety systems and can get 90 times more energy out of the same amount of fuel as a traditional reactor. There's a lot of interest in them, though they're being worked on mostly in China right now. We had a prototype in Oak Ridge in the 60s. I'm not sure when exactly we'll develop them. I strongly suspect it'll be in India just because that's where they have the most fuel and they have the most sort of national security interest in developing thorium-fueled reactors there. They're good stuff. And the other question was vitrification. Is done industrially in France at scale, and it's very successful. So that's something we've looked into at Hanford as well from the nuclear weapons waste. It's certainly it's a totally feasible, good final form for waste headed to the repository.
Yeah, and Australia has their own, they have an artificial rock rather than using glass. They were going to sell that technology because they don't have any nuclear power. But actually, these kinds of things are used for chemical waste as well to pretty much stabilize them and dispose of them.
Just about every nuclear power plant built seems to have regulatory delay, permitting process, and cost overrun and schedule problems. So I wonder, could you address that in looking at the future? Is there any method to streamline such a process? And then the second question is, on the other hand, the U.S. Navy had operate smaller size power plant to power nuclear submarines and aircraft carriers for decades. So why not standardize on that design and mass produce smaller scale nuclear power plants, even on a floating platform that you could just tie it up on the pier?
Yeah.
And how does that compare?
No, excellent question.
That's a fantastic question. There is in terms of cost and schedule delays, there's a wide variety. This is a plot of overnight construction cost of nuclear reactors over time versus different countries. This is the United States, which is pretty vertical. You can see you got lots of delays, lots of schedule issues, lots of high costs. And then if you look here, you'll see places like South Korea, which are consistently building extremely cheap plants on time and below budget. So what did they do differently? They standardized their design. France did something very similar. When France decided to go 80%-ish nuclear, they did it in 10 years, and they standardized their design and hammered them out and did a great job. The United States didn't do such a good job, and we're still experiencing that. Toshiba, Westinghouse just declared bankruptcy, a couple weeks ago because of very long delays on a first-of-a-kind plant. So it can be done right if you standardize, and that's key. So if we want to build lots of plants, we're going to have to standardize. Now, all the currently operating plants, almost all of them in the world, are based on the Naval Reactor Program. So they're based on Admiral Rickover's submarine reactors. That's basically the pressurized and boiling water reactors. Now, obviously, we scaled them up because of economies of scale, but you asked a really interesting question about floating ones. There is an opportunity that some people are looking into of building, basically using shipyard construction techniques to build gigantic, large modular reactors, which you could standardize the construction process of because you're using something like a shipyard and move them all around the world on something like a barge. It's a really interesting idea. There are also a lot of efforts going on small modular reactors right now. There's a company called NewScale operating out of Oregon that has a really exciting small modular reactor that's designed to be sort of manufactured in a factory and then shipped to its location. And again, that gives you the standardization you need to flatten out those cost issues.
And they have a permit for that now, application in with the Nuclear Regulatory Commission. So hopefully it'll move ahead.
Two of the examples you used for safety, the India beach and the Iran
Ramsar.
bath, they seem to be vacation spots, and it seems like the folks going there would not be spending a lot of time there. How do they track those folks to determine that there are no issues?
Oh, they focus their studies on the inhabitants. So there are a lot of inhabitants in Kerala, India. It's not just a resort. And then Ramsar has a year-round population of about 50,000. So those are the people they look at rather than the short term. There are other places that have very high-level radiation around the world. I just chose those two because they were some of the highest. It's a good question. This gentleman up here sort of is.
Get a mic up here.
How difficult would it be to have an emergency generating system, shipboard style, that could be sailed around the world to places with natural disasters and a lack of power? And the second part is, how much blowback is there from coal and natural gas and so forth? do they throw a lot of dirt on your guys' program because they're competitors?
Yeah. Yeah. Can I take the first part?
Yes, of course.
At least. So having a mobile energy source is something that would be really interesting. Actually, it's sort of happened. So after this huge earthquake in Haiti, one of the U.S. Navy aircraft carriers rolled up, which is powered by nuclear reactors, and has a desalination plant on board. And they threw electricity line down and a clean water line, and they just provided, 200,000 gallons of water a day to the area that had been stricken by the disaster. And that's obviously that's a military machine, but you could easily put modular nuclear reactors on a non-military ship that are pretty cheap, and then ship them around as needed. There's also the opportunity to just, if you had the floating reactor thing, you could park it off places that want to purchase energy on a power purchasing agreement, but they don't want to invest in all the nuclear infrastructure. And that's something that has been done in the fossil industry. There's these mobile diesel and natural gas ships that roll up to places. There's one in Iraq, actually, right now. Anyway, so that's, I think, a really interesting and possible idea. What was the other one?
The other one was whether the fossil fuel industry hates nuclear fuel.
They don't say, the thing that they have is natural gas in particular is just cheap. It's much cheaper than operating a nuclear plant right now. You can build it quickly. You can operate it with two guys. It's a jet engine with a throttle. So with the cheap natural gas from horizontal drilling and fracking, at least in the United States, they don't have to say anything because it's just so cheap. And so when people look to build a plant, a lot of them are looking towards what's the cheapest. And without things like carbon tax or other incentives, it's really hard to compete in the United States with current prices. Now, when the United States starts exporting natural gas in a couple of years, things may change because the price might go back up. But I don't think they say too much against that.
The U.S. is a very complex electricity market. Different states have different levels of deregulation, and in some parts of the country like this, like Washington, we aren't deregulated. And when you have deregulation, the idea is to have all sources compete against each other. And that exists in the Northeast and in a fair portion of the Midwest as well. There, natural gas wins almost every time because we have such an oversupply from the fracking revolution. Now, the price of natural gas has actually increased about 35% in the last 3 months. It's very volatile. And the problem with natural gas is that it is so volatile, and many parts of the country are actually coming to rely on that almost 100% for a great deal of their power, and that is a problem. Anytime you depend on one source, that's the pinch in the hourglass. If something goes wrong with that, if the price of natural gas goes way up like it did in California in 2001, everyone is screwed. So you want a diversity, you want to spread the risk, right? Same thing with stocks. So it is not, deregulation is proving to be a failure in some very significant ways, and energy security is one of them. Oh, by the way, the Russians are building a floating nuclear power plant right now, the Alexander Lomonosov, and China is starting to build one as well. The Russians want to use it for offshore to power their oil and gas production platforms in the Arctic, but they also want to lease it around the world, and China's thinking the same way. China is pretty much creating almost a kind of nuclear power kingdom. Almost everything you can think of, even the molten salt and future high-temperature gas-cooled reactors, China's working on them. So it's interesting, and they want to be a major exporter. It's a $700 billion to $1 trillion market in the next 30 years.
Okay, please join me in giving Scott and Nick another round of applause. Thank you guys very much. And thank you, Paula, too, for the kind introduction. Well, I hope you've enjoyed the evening's events. If I measure it by the number of questions we got, I think you hit a home run or two. If you'd like more information about this topic, you can go to the library, the Shoreline Library guides, right? The learning guides at the library on the website, and go look for the GAC, and then this particular event is listed on there as well, and you can find more information on this topic. Please take a moment to complete the survey. Give us some feedback on how well you enjoyed tonight's program, what other topics you'd like to see us participate in, and if there are any students that need to have a piece of paper signed, I'm the person to see as soon as the red light goes off. And is there anything else that I'm forgetting? What? Oh, yeah, you want to make another plug for the Cascadia?
I think maybe everybody heard, but we're Cascadia Climate Action. Our table is over here. It's a calendar embedded in a website, has all climate change activities put in one place. Our next event is next week, April 24th at Naked City Brewery, and it is going to be on sea level rise and global warming, climate change, talking about the effects of sea level rise on the city of Seattle. Also, if you're interested, we have a sign-up sheet for our new little group, Seattle Friends of Fission. And we're the folks that are bringing these talks about nuclear power to many places around town. If anybody's interested in helping, if you have more questions, we're on Facebook. And you can always go to Nick's website with more questions.
And the speakers have both agreed that they will stick around for a couple of minutes because I knew there were a few more hands. We didn't get to all the questions. So keep your questions short. They will keep their answers short, and we will try to satisfy everyone. Thank you very much, and get home safe.